We are surrounded by these invisible systems, these incredible feats of engineering that literally stand guard between us and total disaster. And today, we're going to pull back the curtain on one of the most critical ones out there, ISO 16852. This is the global standard that actually tames fire, stopping massive explosions right in their tracks.
I mean, just think about that question for a second. It sounds like something straight out of a sci-fi movie, right? But it's a very real problem that engineers have to solve every single day. See, an explosion inside a pipe isn't just a fire. It's a pressure wave, a shock front, moving faster than the speed of sound. So how on earth do you stop something that powerful and that fast? Just try to picture it. A massive chemical plant, a huge fuel storage depot, or maybe a pipeline that stretches for miles carrying volatile gases. In places like these, the air itself can become the fuel. All it takes is one little thing. One tiny spark, and a small contained fire can turn into a runaway chain reaction catastrophe. This is the kind of high-stakes world we're diving into.
Okay, so to fight a threat that's this fast and this powerful, you're going to need an equally impressive guardian. And here it is. Meet the hero of our story, the flame arrestor. It's a completely mechanical device. No fancy electronics or anything, but its design is just a marvel of physics, and it's built to do something truly incredible.
This definition right here really highlights the court challenge. A flame arrestor has to pull off two totally opposite things at the exact same time. It has to stay open, letting gas flow through it like nothing's there, but the instant a flame shows up, it has to become a solid, impenetrable wall. The big question is, how does it do that?
Well, the magic, the real genius of this device, it isn't the tough outer shell. It's all about what's packed on the inside. This little component, it's called the flame arrestor element, and it is the heart and soul of the entire system. This is the gatekeeper that separates a minor incident from a full-blown disaster.
And this is where the physics gets really cool. That element is basically a dense web of very small, very specific gaps or channels. So when that huge, hot wall of fire comes roaring down the pipe and hits it, two things happen almost instantly. First, the fire is forced through all those tiny channels, which breaks that one big flame front into thousands of tiny, much weaker flamelets. Second, and this is the killer move, the massive surface area of all that metal acts like a giant heat sink. It just yanks the energy right out of the gas, cooling it so fast that it drops way below the temperature it needs to keep burning. The fire is literally snuffed out on the spot.
This is probably the best way to picture it. It's like a sieve that strains out the fire, but at the same time, it robs the fire of the very energy it needs to exist. It's such a simple concept, but with incredibly powerful consequences. But, stopping a simple fire is one thing. What about that supersonic explosion we were talking about earlier?
And this is absolutely crucial, because in the world of industrial safety, you have to plan for the absolute worst-case scenario. And that means understanding that not all fires are the same. The way they travel through a system creates these vastly different levels of threat.
So on the left, you've got a deflagration. Now, this is a fire that's moving really fast, but it's still slower than the speed of sound. It's definitely dangerous, but it's manageable. But on the right, you have its terrifying older brother, a detonation. This is what happens when the flame front actually accelerates past the speed of sound. It creates this enormous pressure spike and a shock wave that can literally tear metal apart. This is the real monster.
And believe it or not, even within detonations, there are levels. The ISO standard gets really specific about the danger of something called an unstable detonation. They point out it's a much higher level of hazard. This is the most violent, chaotic, and destructive event a flame arrestor could possibly face. So, how do we actually know if a device can survive something like that?
You test it, you push it to its breaking point, and then you push it some more. That is the entire point of the ISO 16852 standard. It's not just some friendly guideline. It's a gauntlet. It's a series of brutal, punishing trials designed to simulate the absolute worst conditions you can imagine, all to prove that a device will not fail when it matters most.
This table gives you a pretty good summary of the main trials. Of course, you have the deflagration and detonation tests to make sure it can stop both kinds of explosions. But look, there are also burn tests. The endurance burning test simulates what happens if a fire just burns continuously on one side, checking if the device can handle that sustained heat. The short time burning test is similar, making sure a stabilized flame can't eventually work its way through. And for every single test, it's pass or fail. There is no in-between.
And this is pretty much what a test looks like in action. You've got this long section of pipe, the test rig, and it's filled with a perfectly calibrated super flammable mixture.
At one end, a spark plug ignites it. Then you have these high-speed sensors all along the pipe, measuring the pressure and the flame speed as this explosion just barrels towards the flame arrestor. The whole thing is over in milliseconds. And at the end, there's only one question that matters. Did any flame make it to the other side?
So, after all that, after surviving the lab, after being put through this brutal testing, where does it all matter? Where do these certified guardians actually go to work? Well, the short answer is pretty much everywhere you find flammable materials.
They are that last line of defense on the vents of those giant fuel tanks, preventing a fire on the outside from ever getting in. They're installed deep inside pipelines to stop a small fire from accelerating into a catastrophic detonation that could rupture miles of pipe. You'll find them everywhere, from pharmaceutical plants to shipping terminals. They are a critical, but totally unseen part of our industrial backbone.
And that number 1 on the screen, that really says it all. In a complex system with all kinds of alarms and shutdown procedures, it often comes down to this one certified piece of metal. It's the final, physical backstop that stands between a manageable incident and an unstoppable disaster.
And that's exactly why ISO 16852 is so incredibly important. It creates this universal benchmark for safety. It means a flame arrestor that's certified in one country can be trusted anywhere else in the world. It guarantees that when a company invests in safety equipment, they're getting a guardian that has already been proven to survive the gauntlet.
So the next time you drive by some sprawling industrial facility, just remember the silent guardians standing watch inside its pipes and on top of its tanks. And it kind of leaves you with a question to think about, doesn't it? What other pieces of brilliant, unseen engineering are out there right now working to keep your world safe?